Welcome to the Predictive Analytics for Marketing course. My name is Dr. Ash Pahwa, and this is lesson 3. Here we are going to cover relationship and distribution in data. In the previous lesson, we covered the data central tendencies and variability. So now we are moving towards relationships and distribution. So lesson 3 is divided into 3 parts. First of all, we will cover covariance and correlation. Then in lesson 3.2, we'll cover rank and partial correlation. And then in the end, in lesson 3.3, we will cover normal distribution. This is the outline for this lesson. In the previous lessons, we covered variance. As you may recall, variance is defined only when we have one set of data, which is called the univariate data. In this lesson, we will examine the bivariate data. It means that we have got two sets of data which are related with each other. So when we compute the variance between two sets of data, that outcome is called covariance. Then we will examine the properties of covariance. And finally, we will examine correlation. Correlation is very closely related to covariance. We will also explore the properties of correlation, which is related to regression. And we are going to cover regression in the next lesson. So now let us start with covariance and correlation. In lessons 1 to 3, we examine the single variable data. The single variable data is called the univariate data. Now, in this lesson and others yet to come, we will discuss two variables, and this is called bivariate data. In order to deal with bivariate data, we need to determine the covariance, then the correlation, and the regression coefficients. So, we are going to examine these things in this lesson. In the previous slide, we explored univariate data and bivariate data. As we learned, bivariate data has two variables. One is called a response variable, and other one is called explanatory variable or predictor variable. All this forms the foundation of predictive analytics. In a given set of data, we seek to determine the relationship between these two variables. Then for the first variable, if we can take any value, we should be able to predict the value of the other variable by using regression. This is indeed the foundation of predictive analytics. So let us take an example. Suppose we have this observed data in which we have the speed of the golf club when we swing it. The second set of known data is the distance the ball will travel if we hit it at a certain speed. So if our swing speed is 100 miles per hour, we observe that the distance it travels is 257 yards. If our swing speed is 102 miles per hour, then we observe that the distance would be 264. This table shows this relationship between the swing speed and the distance the ball travels. So there are 8 observations made of speed and distance. So based on this observed data, we are going to build a plot. Plot of this type are known as the scatter plots. On the x-axis, we plot the swing speed, and on the y-axis, we plot the distance traveled. So now we can see there is a specific relationship exists between these two quantitative variables in our scatter plot. Now, as you may recall, we discussed variance in the previous lesson. Our variance shows us the amount of deviation we have in our data. Instead of defining the variance this time, we are going to define the covariance of two variables. So the definition of covariance is the measurement direction of the linear relationship between the two quantitative variables. So as you may recall, when we were computing the variance, we were computing the deviation from the mean of that variable. But now since we have two variables, we are going to do the same thing for both of them. So first of all, let us examine our data. Suppose we have this data, which is x1, y1, x2, y2, all the way till x and yn. First of all, we are going to compute the mean of x, which will be expressed as x bar. Similarly, the mean of y will be expressed as y bar. Now, if we compute the deviation of all the x values from the mean and the deviation of y values from the mean, as you may recall, we did exactly the same thing when we were computing the variance, but there we had only single variable. Since we have these two variables, we will compute these deviations and then multiply them together. Then we add all of those products. Finally, we divide that sum by n minus 1, where n is the total number of observations. So in the next slide, we will see an example of how to compute the covariance. So here we have some data. Our x values is 6 and our y values is 5. So our second set of observation is x value is 10, y value is 3. So as you can see that we have 5 different observations. So first of all, we will compute the mean of all the x values, which comes out to be 14. Then we compute the mean of all the y values, which comes out to be 7. Next, we are going to compute the deviation of all the x values from the mean. So let us take the first one. The first x value is 6 and the mean is 14. So if we compute the deviation, it comes out to be minus 8. Next, we will compute the deviation in the y values. Since the y value is 5 and the mean is 7, this comes out to be minus 2. Finally, we will multiply the deviation in x with the deviation in y. So multiplying minus 8 with minus 2, we basically get plus 16. Now, if we repeat each of these steps for all the 5 observations, the product of deviations will come out to be 16, 16, 0, 5 and 35. Then we will add all these numbers. So 16 plus 0 plus 5 plus 35 comes out to be 72. And since the total number of observations here are 5, we are going to divide 72 by n minus 1. Since n is 5 and n minus 1 will become 4. So if we are going to divide 72 by 4, we are going to get the value of 18. So the covariance between these two sets of data, x and y value, is 18. And now let us look into the properties of covariance. The covariance of a plus bx and c plus dy is equal to bd, which is the number that we are multiplying x and y values with, and then the covariance of x and y. For example, as we saw in the previous slide, we computed the covariance of x values and y values, which came out to be 18. Now suppose we multiply all of our x values by 5 and leave the y values alone. The covariance between the new x values and y values comes out to be 90. Now, since we multiplied x values by 5, we have also multiplied the covariance by 5. So 18 multiplied by 5 also comes out to be 90. Now suppose if we multiply all the x values by 5 and also multiply y values by 10 and then compute the covariance between them. Here I have multiplied x values by 5 and y by 10. So the product of 5 times by 10 comes out to be 50. So now if I multiply 50 multiplied by 18, we are going to get 900. So that is the new covariance. So if the values that we have are multiplied by a certain constant, the values of the covariance will also increase. Here are some results which enables us to see the covariance, which is unlike correlation, doesn't have to fall between -1 and +1. We have not studied correlation yet, which is the next topic, but correlation values always remain between -1 and 1. This, however, is not the case with covariance. Covariance will go up or down depending upon how big our numbers are. So covariance is not a metric which gives us a real sense of how negatively or how positively these two variables are related. If the x and y values are large, then the covariance, of course, will also become large. For example, if somebody says that the covariance is a -100, it does not give us a real sense of how negatively these two variables are related. Fortunately, we can solve this problem with correlation, which we are going to discuss next. Now let us explore correlation. Correlation is a very important topic in statistics, and correlation is being computed by dividing the covariance by the standard deviation of x values and the standard deviation of y value. So correlation is another metric that gives us a value only between -1 and +1. So what is the definition of correlation? Correlation measures the strength and the direction of the linear relationship between the two quantitative variables. These particular metrics are usually represented by a small letter r, which can vary between -1 and +1. So to compute the value of correlation, we just divide the covariance by the standard deviation of x and the standard deviation of y. In the next slide, we will take the same example we have been using before and then compute the correlation of that data. Let us now compare the covariance and correlation. As we have learned, the covariance is the deviation from the mean of the x values multiplied by the deviation from the mean of the y values. Then we multiply them together. Then we are going to sum up all the numbers and divide the sum by n-1. So that gives us the covariance. Now to compute the correlation, we just divide the covariance by the standard deviation of x and the standard deviation of y. So whenever we have the correlation of the population, it is being represented by the Greek character rho. It represents the correlation of the population. As I mentioned before, a small letter r is used to represent the correlation of a sample. So now let us take the same example and compute the correlation. When we were computing the covariance, we saw this example where we computed the mean of x and y values, then we computed the deviation of all the x and y values from the mean values. Finally, we multiplied these numbers together and added all of them. So 16 plus 16 plus 0 plus 5 plus 35 comes out to be 72. Then when we were computing the covariance, we divided 72 by n-1, which was 4, and we got the value of 18. But now to compute the correlation, we are also going to divide this number 72 not only by n-1, but also by the standard deviations of x and y. We have to compute the standard deviation of x and y beforehand. So as you recall, we computed the mean of x, which is 14. We also computed the mean of y, which is 7. We also computed the standard deviation of x, that is 6.20, and the standard deviation of y, which is 3.39. Now let us compute the correlation. To do this, we take 72, which is the sum of the products, and then divide that thing by 4. And then again divide that thing by 6.20, and then again divide that thing by 3.39, which are the standard deviations of x and y. So as you can see now that we are going to get the number of 0.855. So the correlation is always going to be between -1 and +1. And closer it is to +1, the stronger the correlation is between those two variables. Now let us look into different correlation values. There are total 8 graphs here, and we will go through each one of them. Let's take the first one, which is A. In this instance, there is a perfect correlation between x and y values. So we can see a straight line, and in this case, the correlation is going to be +1. Now let us take B. Here we can see that the correlation has dropped from 1 to 0.9. Meaning that the data is not as strongly related as was the case in A. Now in diagram C, we see that the value of R, which is a correlation constant, has dropped from 0.9 to 0.4, and we see that the relationship between X and Y values is not as strong. Then in diagram D, we have a very, very strong correlation, but in this case, the value of R is -1. A -1 means that the value of X is increasing and the Y value is decreasing. But they have a very strong relationship with each other, and the correlation in this case is -1. Similarly, if our correlation is -0.9 as shown in diagram E, we see the values of X and Y's are not that strongly correlated. Let us look into diagram F. Now, if we have the R value of -0.4, then of course there is even less relationship between X and Y values. Now, if we look into diagram G, we can see that R is close to 0, meaning virtually there is no relationship between X and Y values. Now, if we look into diagram H, we see there is a quadratic relationship between X and Y values. In this case, R is also 0. So, R is a correlation constant only indicates the linear relationship between X and Y values. If R is equal to 1, it means as the X and Y values, as X value is going to increase, Y value will also increase. And if R is -1, then as the X values are going to increase, Y value will decrease. Now let us examine the properties of correlation coefficient. Unlike covariance, correlation varies between -1 and +1, as we saw in the previous slide. And if R is greater than 0, it means that as we increase the value of X, Y values are also going to increase. And if R is negative, then as the X value increase, Y value will decrease. The more that X and Y are linearly related to each other, then closer R will be to -1 or +1. With the real world data, we rarely encounter +1 or -1 correlation between two sets of data. If we see there is a strong relationship between X and Y values, we can see that the correlation will be somewhere around 0.7 to 0.9. But virtually never the correlation coefficient is going to become +1 or -1 with the real world data. Now let us examine another property of correlation, that is correlation of a+bX with c+dY is equal to the sign of B and D and the correlation of X and Y. So unlike covariance, if we multiply these numbers with any constant we choose, the correlation will not change. And then that is the beauty of correlation. Correlation will remain the same even if we multiply these variables with a certain constant. For example, if we have X and Y values and we computed the correlation to be 0.855. Now let us multiply all the X values by 5. So our first value will become 6 multiplied by 5, which comes out to be 30, and so on. Now if we compute the correlation between X multiplied by 5 and Y, we see it is still 0.855. So no matter whether the value goes up or whether if you multiply certain variables with a certain constant, correlation remains constant. Similarly, if we take the correlation of a variable which is X multiplied by 5 and Y multiplied by 10, the correlation of this set of data again will remain 0.855. So what we have learned from these exercises? Basically, that correlation represents the linear relationship between the two variables. If the correlation constant between the two variables is high, which means it is closer to +1 or -1, then we can conclude that there is a linear relationship exists between these two variables. This is a very important conclusion, and we are going to use it in the next lesson when we are going to study regression. Regression is another way by which we can compute the relationship between the two variables. Now, if we determine a relationship exists between two variables, it does not necessarily mean there is a causation. So, although we may find two variables which are highly correlated, it does not necessarily mean that one variable is causing or impacting the other variable. So, correlation does not necessarily prove or equal to causation. For example, suppose our air conditioning bill goes up and the crime rate goes up as well. If we try to match the data of air conditioning bill with the crime rate, we may possibly find there is a high correlation. But common sense tells us that it is unlikely one is causing the other. So we have to investigate further to determine what is happening here. A lurking variable, which is the third or invisible variable, exists. In this case, it is temperature. As the temperature goes up, the air conditioning bill also rises. As the temperature goes up, the crime rate also rises due to discomfort. During the winter time, people may be less volatile and are likely to go out and commit crimes. But as weather becomes balmy again, the crime rate often rises. So temperature is a lurking or the invisible variable here. Though we can find correlation between two variables, it does not necessarily mean that there is a causation between these variables. So that is the end of lesson 4. Let me summarize what we covered here. We started with bivariate data where we have two variables. We computed the covariance between two such variables. Then we examined the properties of covariance. And finally, we explored correlation. Correlation is defined based on covariance, except that we divide the covariance with the standard deviation of x and y to get it. Correlation is a very important concept in statistics, and the value of the correlation varies between -1 and +1. If the value of the correlation is close to either +1 or -1, then we say that we have a linear relationship between x and y variables. Such a relationship can be explored using regression, which we will address in the next lesson. We also came to understand why correlation does not necessarily is equal to causation. There may be a lurking variable or an invisible variable present that must be accommodated. Thank you. I will rejoin you in lesson 5.